Hi there everybody, welcome to the Goodest Education YouTube channel, and today we're going to be talking about differentiation. I am using some reference materials from some Edexcel A-level textbooks, which future me on the YouTube video put a picture of what that looks like, so people know what I'm referencing. Because I want to make sure I could just talk about differentiation on how I use it, but that probably isn't the best idea because I may go too far, it might get slightly confusing, and I'd rather teach what I exactly know is on the syllabus of A-level maths, because I did my A-levels in 2012 and 2011, 2012, so 8-9 years ago. Everything's changed around since then. What used to be maths for me is now further maths, and what used to be further maths is now maths. And something that I learned matrices and like further pure 4 module, and they're now just in further pure 1, so everybody learns them, whereas not everybody learned matrices before. But which is probably the way it was, because it's probably the way it should be, because if you do any sort of scientific degree, you will need to learn matrices, so it probably should be an A-level. But anyway, okay, so differentiation. So at GCSE, people learn how to find the gradient of a function. So there's a function y is equal to x squared. You'll find a gradient along this curve by basically just trying to draw the tangent, so this red line here, at any point, and trying to get the gradient and try to get it to go through that point as well as you can, and trying to get the gradient at that point to match as well as you can. So you would draw that, and then you would work out the gradient of this red line, and then that would be a good estimate as to what the gradient is at that point. But if you want to have a nice way of working out the gradient at multiple points, you don't want to be drawing lines all over the function and trying to find it out. Because A, it takes a long time. B, it's probably not very accurate. Depends on how well you can draw a line, which sometimes isn't great. So what the idea is instead of doing that, we want to try and find a function, an algebraic function that describes the gradient of this curve. So we can use algebra to find the exact point. So what you would do is, for example, if you drew this red line across using points A and B, so you draw a line across there, the gradient is a very good match. But what you do is if you move B closer and closer and closer to A, the difference between A and B gets really, really small, and then the eventual red line that you would draw across A and B would estimate the gradient at A to a good degree. But, so if you did that, at the points A and B, let's say that the difference in the horizontal coordinate, the normally x, is h, so we take a step h in the x direction, and then the difference between A and B would be the function value at x0 plus h, which is what it is at B, minus the function value at x0, so it would give this distance here. And if we want to move A and B closer and closer together, the way to do that is to reduce h. So it's very, 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 very small. So small that it tends towards 0. So what we call this the gradient function, or the differential. Which, if you have a function f of x, we would call the differential of that f prime or f dash of x. But if you tend to use y, the way to write it is dy dx, because it measures the rate of change of the function y as a parameter, as with respect to x. So to put this into a nicer form, what we would do is we want the gradient of this, which is change in y over change in x. So differential of x is going to be equal to the change in y, which is f x0 plus h minus fx0 over the change in x, which is h. And we want to make it so a and b get closer and closer together. So we take the limit of this as h tends towards 0. And this function here is what's known as the differential from first principles. So to work out the differential of any function, you can do that by using this equation. And it'll work for anything. There are some equations that it might be very, very messy for, but it should work. So, for example, let's do an example. An example could be the point A with coordinates 4, 16 lies on the curve with the equation y equals equal to x squared. At point A, the curve has a gradient of g. Show that g is equal to the limit as h goes to 0 of 8 plus h. So using what we just did, we would write... Oh, I'm using the wrong one. Don't use the rainbow one. Weird. So dy by dx is going to be equal to y at b. Well, okay. Well, y not all, which is going to be f of what f of x or y at a plus h. So we would write x plus h squared over minus y at a, which is going to be x squared all over h. And then take this limit as h goes to 0. So then if we times this out, we're going to get x squared plus 2 yep, okay. So x squared 2xh plus h squared minus x squared all over h, which is equal to the limit h going to 0, and then the x squared is cancelled, so and then we could divide by h, so we're just going to be left with 2x plus h. Now we're at x is equal to 4 because the point A has coordinates 4, 16, and so we can sub that in, and then this is going to turn into... I'll put even writing a whole other line for that. That's going to turn into 8 plus h, which is what we wanted up here. So then we want to deduce the value of the gradient, g. So we're going to let h go to 0. And quite easily, h is just 0. So then this is 8. So then the gradient of y equals x squared at 416, well, at 416 is 8. So let's prove from first principles that the derivative of x to the cube is 3x squared. So using this again, we're going to have... Let's use f of x this time. So is equal to the limit of h going to 0 of x plus h cubed minus x cubed all over h. When the fun of timing out cubes, you're going to get x squared plus 2xh plus h squared times x plus h. You could just use binomial for this, but... And then that is going to be x cubed plus hx squared plus 2x squared h plus 2xh squared plus h squared x plus h cubed minus x cubed for h. Do that. So then we're going to group the like terms, so the x cubes are going to disappear. And then we're going to have, so x 3x, squared h plus 3 h squared x, and we've done hx squared, hx squared there, sorry I get mixed up, then xh squared, xh squared plus h cubed all over h. And then we're going to cancel out these h's, so that's going to disappear. That's going to go to 1, and then that's going to go to 2. I remember all of this, I haven't written it, but all of this is taking the limit as h goes to 0. So if you then take that limit as h goes to 0, this is going to disappear here. And this is going to disappear here. So we're going to get f of x is 3x squared, because that's the only value that's left over as h goes to 0. And that's what we wanted to show. So what you might notice, so x cubed differentiated goes to 3x squared, is that there is a pattern there for polynomials. For all real values of n for a constant a, if y or f of x is equal to a x to the n, then f of x, well, f prime of x, the differential, is going to be equal to a. The n comes down in front of the x instead of up there, and then you drop the power by 1, so n minus 1. And this is always true for all polynomials. It's quite easy to remember. You can always you can find this equation by algebraically putting it into the differentiation by first principles. So if you forget it, you can find it again. So, and it's always hard to remember sometimes for certain powers. Everybody makes mistakes with these. Let's just do a few examples. I'm sure even lecturers and teachers have made mistakes here. So find dy dx when y equals these. So for 7x squared, for 7x cubed, the 3 is going to come down in front, so it's going to be 7 plus, well, times 3, and then x, 3 minus 1 is 2, which is going to be 21 x squared. And then for b, we're going to have minus 4 times a half, and then you're going to have x to the power of a half minus 1, which is minus a half. So you can also write this though as minus 2 1 over squared, because the reciprocal, when you have a power that's negative, it's the reciprocal, so you flip it, and then to the half, the power of a half is the square root. So for 3x to the minus 2, the minus 2 is going to come down, so you're going to get minus 6, and x to the minus 3. It is a bit interesting that I've done that. So first you have to, so for d here, first you're going to have to cancel it, so x, well, 8x to the 7 over 3x is equal to 8 over 3 x to the 6. And then the differential of that, 6 is going to come down, which is going to make this 16 x to the 5. And then for this one, you're going to have to simplify it. So the square root of 36 x cubed is going to be equal to 6 x to the 3 over 2. And then the differential of that is going to be 6 times 3 over 2 is going to be 9 x, and then 3 over 2 minus 1 is a half. So 9 times x to the half, which again is 9 square root of x. So finding the gradient at here a is great, but the differential is going to give you the gradient. But what if you want the normal at that point? So the equation of a line is, if you have a point a at x1, y1, a straight line equation that goes through this point is y minus y1 is equal to m, where m is the gradient, x minus x1. And you can replace that m, so m is equal to dy dx. Now, this is the equation of this red line here, going across here. But if you wanted the normal to that, the normal, which doesn't really get called anything, we just have to write the normal. It doesn't have a nice symbol, but is equal to the reciprocal times minus 1. So it's minus 1 dy dx. So if we did a quick example, so find the equation of the normal to the curve, this equation at the point where x is equal to 4. So y is equal to 8. It's always a good start to rewrite the equation with all the powers written out properly. So 8 minus 3 x to the half. So then dy dx. So anything that doesn't have an x, when you differentiate it, just disappears, because this 8 is technically a x0 minus 3 x to the half, because anything to the power of 0 is 1. So this is the same thing. And when you differentiate this, the 0 is going to come down and then go down by minus 1. And then anything times 0 is 0, so this just disappears. So when we differentiate that, we're going to get minus 3 times a half x to the power of minus a half. So minus 3 over 2 x to the minus half. So then the gradient of this at 4, so one way that people write this is dy dx, and then a line going down, x equals to 4. So then this means the dy dx evaluated at x is equal to 4. So then we substitute 4 in, so it's going to be minus 3 over 2. Then 4 to the power of minus a half, which is 3, 2, and then the reciprocal, so it goes into the denominator, and then the square root of it is 2. We have 2 times 2, and this is 3 over 4. However, this is the gradient at this point, which isn't what we want. We want the normal. The normal is the reciprocal, which is 4 over 3, and then times by minus 1. So then the normal at this point is minus 4 over 3. And that's how you get from the gradient to the normal. One great thing to do is to find the gradient, but it can be used for so much more than that. And so if we look at this example here, we're going to talk about local minimum and maximums. And they're called local minimum and maximums because there may be... So this, we're looking at this part of the function, say, between points A and B. But it might be, because the function goes on forever, that there may be an even bigger maximum turning point. So that would be the global if it's the highest over the whole function. But we're going to talk about these local points, so the points that we're just looking at. So when a curve changes direction, so here it's increasing, the gradient is equal to 0 here. At this point, and then it starts decreasing, and here, and we call that a local maximum. And then again, another example is it starts decreasing, the gradient is decreasing, and then the gradient is equal to 0. And then it starts decreasing again. It hasn't turned, it's just carried on decreasing. So we call this a point of inflection. And then the gradient coming towards B is decreasing, the gradient is equal to 0, and then the gradient increases. It becomes positive and starts, so the function starts going up. So, and these are all called stationary points. So a stationary point is when the gradient, or f-x, or f'(x), is equal to 0. But the nature of that stationary point you can find by looking either side of the point. So for a local maximum, just before the stationary point, the gradient is positive, as we can see here. So the gradient is positive, it goes to 0, and then it goes negative. For a local minimum, it starts off decreasing, starts off negative, hits 0, and then starts to increase again. And then this point of inflection, you can either have it when the gradient decreases, hits 0, and then decreases again, or equally you can have it the other way, so it increases, hits 0, and starts increasing again. So a quick example of that is find the coordinates of a stationary point on the curve with equation y is equal to x to the 4 minus 32x. So to find a stationary point, we first need to know what the gradient is. So gradient dy dx is going to be equal to 4x cubed minus 32. But how we find a stationary point is when the gradient is equal to 0, which means that dy dx is equal to 0. And then we solve this equation. So you're going to have x cubed, move the 32 over, and then divide by 4, going to be 8. So then x is going to be equal to 2. So then, and then you want to find the y coordinate, corresponding y coordinate. So y is going to be equal to 2 to the 4 minus 32 times 2, which is going to be equal to minus 48. So now that we've found a stationary point, which is at 2 minus 48, working out where it is without drawing it doesn't really give us any indication. So what you could do, so if you had dy dx is equal to 4x cubed minus 32. If you substitute in values either side of the point, so if you put in x equal to 1.9, then dy dx is equal to minus 4.56, which is negative, so it means that the gradient is decreasing just before. And then if you put in 2.1, dy dx is equal to 5.04, which is positive. So just before the point is decreasing, it hits 0, and then it's increasing, which is like this example here. So it's decreasing, it's a stationary point, and it increases again. So this point here is a local minimum, which gives us a bit more example of what it looks like at that point. Now, if you don't want to sub in numbers, it's not a very elegant way of doing it. What you can work out is because differentiating gives the rate of change of one coordinate with correspondence to another coordinate, you can find the second derivative, so you can differentiate again, and that gives you the rate of change of the gradient. So if the rate of the change of the gradient is positive, it means that the gradient is increasing. If the rate of the change of the gradient is negative, then it means it's decreasing. So find coordinates of a stationary point, well, of the stationary points on the curve with equation y is equal to 2x to the 3 minus 15x squared plus 24x plus 6. So working out the gradient, dy dx is going to be 6x squared minus 30x plus 24, just using the rules that we used previously. So then we want this equal to 0 because we want to find the stationary points. And this is just a quadratic. So there's a factor of 3 running through here. So actually there's a factor of 6 running through here. So you can take a 6 out. Then it's going to be x squared minus 5x plus. So then we can. So we're going to have. So we want minus 5 by adding them together and 4 by timesing them. There's going to be minus 4 minus 1 equal to 0. So then solving this quadratic, we're going to get x is equal to 4 and x is equal to 1. So when x is equal to 1, we're going to get 2 minus 15 plus 24 plus 6, which is equal to 17. And then when y is equal to 4, we're going to get 2 times 64 minus 15 times 16 plus 24 times 4 plus 6, which is equal to minus 10. So then the stationary points rid of this. The stationary points are at 1, 17, and 4, minus 10. So to find the nature of these stationary points, we want the second derivative. So we're going to derive dy dx again. So we put d squared y over dx squared. The reason why it's written like this is just notation. Like, because if people wrote d squared y d squared, well, d to the 2 y d to the 2 x, people would just cancel the d if they weren't paying attention. If they just looked at it as a fraction, so it's just written like this, just to make sure no mistakes like that happen. So I'm going to differentiate this again. We're going to get 12x minus 30. And so what we're going to do now that we have the second derivative, we're going to substitute these values for x in. So at 117, the second derivative, x is equal to 1. Therefore, the second derivative is going to be equal to 12 minus 30, which is negative at minus 18. So when the so this means that the gradient is decreasing. So it means it's a local maximum point. So for x is equal to 4 square y dx squared is equal to 12 times 4 minus 30, which is equal to positive 18, which is more than 0. So therefore, this is a local minimum point. So You may get instances where this is equal to 0, or the second derivative is equal to 0, which means that it's going to be a saddle point. It's going to be a point of inflection. So you need to do a bit more investigation to see on the other side of the point to see which way it's going. Whether the saddle point is going to be like that, or the saddle point is going to be like that. This is great and everything, working out the gradients of curves, but you know, how useful is that in real life? It's only really useful in maths. So let's talk about a model, so a real world situation. So you could think of dy dx is equal to a small change in y over a small change in x for something. So it represents the rate of change of y with respect to x. So if you replaced x and y with some real life quantities, you can use the derivative to model a lot of real life situations involving a rate of change. So example, if you had a load of if you had a volume of water in this water tank, and so you're pouring water into it, but equally you're taking water out. So the rate of change of the volume of water is always going to there's always going to be a rate of change of this because the amount of volume of water in the tank is changing. So if you were to write, so this time, because it's a real life situation, we want to write with respect to time, because time is how we measure the passing of things. So the rate of change of the amount of water in here would be written as dv by dt. So the rate of change of volume with respect to time. So, and for the units of this, because it's a real life situation, the units of volume are going to be meters cubed, and then by time, there's going to be the rate of change is going to be meters cubed per second, or liters per second, or any unit of volume that you want to use, but it would have that form. So let's do an example of this. So this reminds me of a question that I had in my A-level exam. So this is the sort of question that they might give you, so it's worth working out. So a large tank in the shape of a cuboid is made to be 54 meters squared of sheet metal. The tank has a horizontal base and no top, so it's not got a lid on it. The height of the tank is x meters. Two opposite vertical faces are squares. Show that the volume of the tank is given by that equation. So what's always best to do is we want to first draw this out. So we're going to have a tank here. It's not going to have a lid on it, so we're going to have these face there, face there, face on the other side, and then a face on that side, and then a face at the bottom. So, looking at the information that it gives us, we've got this amount of sheet metal here. That's going to be useful. So it's a horizontal base with no top. The height of the tank is x, right? So then the two opposite vertical faces, which is going to be this one and what would be the one over here, are squares. So it means that this distance here is also x. So then, if we call the length of this y, which is something that we don't know, so the total area, we want to know what the total area of this is going to be in respect to x and y. So the total area, we're going to have, so this face here and this face here have an area of x squared, and there's two of them. So 2x squared. And then we're going to have this face at the front, the face on the bottom, and the face on the back. But we don't have a face on the top because it's not got a lid. And that's the area of those is going to be y times x. we're going to have plus 3xy. But the thing is that we know that the total area has to be 54 meters squared because that's all the sheet metal that we have. So the total area is going to be equal to 54. Which means that we can work out what y should be, because y is what we don't have. So if we rearrange this, we're going to have y is equal to 54 minus 2x squared all over 3x. And the volume of this tank is going to be x squared, because it's the area of this end of this face, and then times it by y to get the volume. And we know y, because we just worked out from the total volume, from the total area, sorry. So this is going to be x squared 54 minus 2x squared all over 3x. So then if we times that all out and take out a factor, well, we could just times it all out. We're going to get 18x minus 2/3 x cubed, which is what we wanted here. This is what we need to show the volume. So that's done. So the next part is, given that x can vary, use differentiation to find the maximum or minimal value of the volume. So this is similar to when you find a maximum or a minimum of a graph, except this time we're not working with f of x or y, we're working with this volume v, but it's the same principle. So when you want to find the maximum or the minimum of something, you just want to differentiate it and then set that differential to 0. So we want this we want the differential with respect to x because x can vary. So we want dv dx is going to be equal to 18 minus 2x squared. So now we want to find the maximum, we want to find the positions of the stationary points, the maximum and the minimum. So we want to set this to 0, which means that x squared is going to be equal to 9. Therefore, x is going to be equal to plus or minus 3 because it's a square root. However, we're dealing with real parameters here, and there's no such thing as a negative length. So we're going to take the positive value. So we're going to get x is equal to 3. So then, when x is equal to 3, the volume is equal to 18x minus 2/3 x cubed. So we want to put 3 into that. So we're going to have 18 times 3 minus 2. Oh, that shouldn't be an equals. Minus 2 over 3. And then 3 cubed, which is equal to 54 minus 18, which is 36. So v equal to 36 is either a maximum or a minimum, but we don't know that because we haven't investigated what that stationary point looks like. But instead of drawing out this equation here, we can work out dv by dx squared. So dv by dx is dv by dx is equal to 18 minus 2x squared. So we're going to differentiate that again. So we want dv by dx squared, which is equal to minus 4x. So then we want to sub in our stationary points into here. So our stationary point was x is equal to 3. Therefore, the second derivative is equal to minus 12, which is negative, which means that b equals to 36 is the maximum, which is what we would expect, but you've got to prove it. So remember that if dv dx squared is negative, we're going to get a maximum. But if dv, the second derivative of v is positive, it would be a minimum. So there are plenty more examples, but that is, you're going to use very much the same mentality and the same process of doing it. The only thing that would where the difference would come from, the hardest part of questions like these is formulating the initial equation. Sometimes it might just go, oh, here's this information about this tank, find the maximum volume. It won't give you any steps in between then, but in between the question and that bit. So it's always a good idea to sketch it out, like we did here. Find an equation for anything that you can find that's relevant. So the area, because without the area, you wouldn't, the total area. Because if they give the total area in the question, that it's going to be useful. It's very rare that it's just a red herring. You're going to need to use it. So we found an equation for the area, which was useful to eliminate y, so we only had v in terms of x. And then, so we have an equation for v, and then you just differentiate and go from there. Okay? Oh, that makes sense. So future me in this, where you takes a summary of everything that we've done and just put it on the screen. So then if people want, they can pause it and have a read of it. I'll take a screenshot of it and it might be useful for them. I hope that was useful. That was basic differentiation. There's a whole lot more to differentiation. And there's a whole lot more. There's something called anti-differentiation, which is integration, which is a whole set. It's basically differentiation backwards, but that has different uses and very good uses, and I use it all the time in my work. So calculus is very useful. You will use it in any science degree that anybody does, any engineering, any physical sciences or engineering jobs or anything like that. Chances are you will need to use calculus. Calculus is always just good to know. So okay, I think that's going to be me. So if you were lurking or if you were watching this, thank you very much for being here. I'm going to edit this down and put it on my YouTube. And so if there's any questions on this, leave it in the comment section below. Follow the channel, follow the Twitch channel, follow the YouTube channel, and there'll be plenty more where this comes from. There'll be a few more lessons. If you want any particular subjects teaching, just let me know and I'll get around to it. So thank you very much for watching, and bye.